My name is and I'm going to present the results of my work at St. Petersburg State University. But firstly, let me thank the organizing committee for this opportunity to provide, to give a talk. My work is about polarization states of gravitational waves. And I present the method which allows us to get information about polarization states of an incoming gravitational wave detected by interferometric antennas such as working Virga liner interferometers. A gravitational wave is characterized by polarization states which can be tensor or scalar. For example, in the case of general relativity, they exist on the tensor, cross, and plus polarization states. But the modern scalar tensor metric theories predict the existence not only tensor, but also the scalar longitudinal or transverse polarization states. And the key question in my work is how to determine polarization state. It's possible when we consider how an interferometric antenna works. Polarization state can be represented as a displacement of test bodies responding on an incoming gravitational wave. Here are depicted first two tensor plus and cross polarization states, and then scalar transverse and scalar longitudinal polarization state. On the same principle of really moving test bodies, an interferometric antenna is based. It has two orthogonal arms with test bodies at the ends, and an incoming gravitational wave displacing test bodies gives a so-called strain, which is the difference between lengths of arms normalized by the initial length of the antenna arm. When we consider general strain can be decomposed as antenna response functions weighted by antenna waveforms. Antenna waveforms are crucially dependent on the processes producing this gravitational wave and depend on the time. But antenna response functions doesn't depend on the time. They depend only on the position of the source relative to the antenna. These angles are azimuth and zenith angles in horizontal coordinate system of the antenna. We can consider more closely antenna response functions. For example, in tensor transverse gravitational waves, antenna response functions, which are presented here, for convenience, we can represent these functions in 3 dimensions as beam patterns of the antenna. We can see clearly that beam patterns are different for tensor plus and tensor cross polarization states, which means that a typical 2-arms interferometric antenna allows us to distinguish between tensor plus and cross polarization states. But when we consider the scalar waves, antenna response on scalar wave, we see that antenna response functions are different only by a sign. Therefore, antenna beam pattern are the same for scalar longitudinal and scalar transverse polarizations. To solve this problem, there were proposed a modification of interferometric antenna, which called one-arm interferometric antenna. It doesn't work now, but it is proposed to work in the future. One-arm antenna is capable to distinguish between scalar longitudinal and scalar transverse polarization states, because antenna response functions are different for these polarizations. Now we can see that antenna response functions, by means of antenna response functions, it's possible to recognize polarization state of gravitational wave. And we can apply this information to the practical measurement of the state. A typical gravitational wave strain, which is h, it depends on the position of the source in the sky and time. And theoretically, it can be decomposed on the waveform, which depends on the time, and independent part, which I call G factor or geometrical factor, which depends only on the position of the source in horizontal coordinate system of the antenna. So when we have a network with at least two working interferometric antennas, we can consider the ratio of the measured strains at each antenna, H1 to H2, which should be equal to the calculated geometrical factor for the corresponding polarization stage of gravitational wave. So here, geometrical factors, what there are, for scalar polarization, the geometrical factor is just equal to the scalar antenna response function. And for pure tensor class or tensor cross polarization, the geometrical factor will be equal to the antenna response functions. But when we consider the mixture of polarizations, so for example, tensor polarization class and cross, there should be calculated multiple, should be calculated the method of factors. So now when we have a network with three working antennas, as now working like a Virgo, the position of the source can be determined, and it gives us the coordinates of the source in equatorial as well as in horizontal coordinate system of the antenna. So it means that for the source, we can calculate the G factors for the proposed polarization states and calculate the ratio of the geometrical factors for these states, and then the comparison of the calculated geometrical factors with the measured ratio of the states allow us to make a conclusion about the real polarization state of an antenna with an observation layer. So now we have like Livingston, Henman, and Virgo in Italy antennas. So this is a network with three working interferometric antennas. And there were detected two events in August. And here I provide the calculations for the few tensor plus polarization states, for scalar longitudinal or transverse polarization state. It means that, as we remember, antenna response function doesn't allow us to distinguish between scalar longitudinal and transverse polarization states. So this calculation is for the same scalar longitudinal or transverse. And here are some simulations in the case when there were one arm interferometric antenna. So here just some simulation for this case. The first and second events in August 2017, and these results should be compared with observations. And for example, in the case of first event, the observation is approximately give us this simulation. So the ratio of G factors, G LIGO and to Hanford, and G LIGO Livingston to Virgo, and Virgo to Hanford, give us this. And the predictions represented here, but we see that the observation doesn't match to the predictions. It means that we should make the next calculations for the mixture of polarization states. So, for example, for mixture of tensor polarization states, to make conclusion about the real polarization state of gravitational wave in this case. So, and here is my conclusion about this research. So, the terms interferometric antenna allow us to distinguish between tensor and scalar, as well as tensor plus and cross polarization states. And in the case of working one arm interferometric antenna, it's possible to distinguish between scalar longitudinal and transverse polarization states. And the method allows us to recognize polarization state in gravitational wave, but there should be calculated the mixture of polarization states in the case of gravitational waves detected in this year. And an important question about the polarization states, that the determined polarization state allows us to test the theory of gravitation, which, as I said, there are some modifications of general relativity, for example, scalar tensor theories, as well as field theory. So this is the main conclusions. Thank you very much for your attention. And some questions about this work you can see in these articles. So thank you very much, and please, if you have questions.
Question? Are you going to consider mixed polarizations to test, to use the last two events to test mixed polarizations?
I just can make some simulations and to provide some templates which should be then compared with the observations which are here, is approximately. But when we say about when we speak about the tensor polarization states, the formula to provide this calculation is given here. So I mean that it may be a further work in this direction to the observation in this year and the future observations.
I just want to remind you and everybody that the data is public for all the detections that have been published. So you can do that kind of study.
Yes, it's relevant to that.
Other question? Thank you, the speaker again.